Curiosity is looking for the existence of organic compounds on Mars. Organic compounds are what you think they are. They're compounds associated with life, but they've come to take on a technical definition too. The technical definition is here on the screen. An organic compound is any compound that contains the element carbon, except for two. There's two exceptions. One is carbon dioxide and the other is carbon monoxide. The reason why it is we don't consider these two compounds organic is because they are, technically speaking, completely oxidized. The carbon is completely oxidized. What that means is the carbon really doesn't have any energy available for living systems left in it. So organic compounds then, or living things, are not really made out of carbon dioxide and carbon monoxide as their components. Carbon dioxide and carbon monoxide can be used to make organic components, but you're not made out of CO2, for example. So this is then the key to understanding what living systems are: carbon-based chemistry. But what do we mean exactly by compound? That's the next question. What exactly is a compound? Again, compounds are things you've heard of before. They're related to molecules, and you probably know something about this, and you probably should because you've taken a chemistry class. But basically, the technical definition of compound is this: a chemical compound is any substance composed of two or more different elements in a fixed proportion. Now here's an example. This is water. Notice I'm not showing H2O. That's the molecule of the compound water. In this case, the compound is a substance. It's this stuff, the liquid at room temperature or general temperatures on Earth, on the surface of the Earth. And it is, again, something that contains two or more different elements in a fixed proportion. And again, what do we mean by fixed proportion? Well, again, water always has two hydrogens for every oxygen. Okay, so that's great, but now we need to know this. What in the world is an element? Okay, if an element, elements make up compounds, then what's an element? And again, many of you already know this, but just I want to make sure we have the technical definition down. The technical definition of an element is any substance that cannot be broken down by normal chemical means into another substance. And this is part of the phrase that you need to focus on: normal chemistry. You can change elements from one form to another using nuclear physics, nuclear changes, but that's not chemistry, that's physics. So in this case, we're talking about normal chemical change. An element is something that cannot be changed from something to another thing that's simpler without actually going in and blowing apart the nucleus in some way. So not blowing it apart necessarily, but changing it in some way to be more specific and accurate. So this is also, again, an element, but not an atom. Notice that we always say the periodic table is a table of the elements, not a table of the atoms. Why is that? Well, because an atom is not an element. An atom is something like this. This right here, what is that? And what is this? And what are these blue things? And what are their charges? Again, you've seen all this before. You probably know that this is a proton, and its charge, listed here as plus, is actually technically +1, 1 unit. This is an electron, and its charge is -1 unit. These light blue things are neutrons, and they have a charge of 0. So what you're looking at here is an atom of the element hydrogen. This happens to be the most common type of atom of hydrogen. This is also the most common form of another element. In this case, the element is carbon. How do we know it's carbon? Because it has six protons in its nucleus. How do we know it has 6 protons? Because in this picture you can't see there are 6 protons. We know there must be because there are 6 electrons. If you count all of these up, there are 6 of them. So that tells us then that there must be 6 protons. How do we know that? Because of the definition of an atom. So these atoms then of hydrogen and carbon are representative of all atoms. An atom, technically speaking, is the smallest electrically neutral unit of an element. So in other words, suppose we go back up here and suppose we look at this lump of coal. This is the element carbon. If I cut this lump of coal in half, then I have still the element carbon. I cut that lump in half, and I cut the remaining lump in half, and the remaining lump in half, and the remaining lump in half, and I do that indefinitely over and over and over again. Eventually, I'm going to get to a smallest unit. I'm going to get to something that is this. And if I can't cut this any further, then it's an element. Okay? Or I'm sorry, it's an atom, pardon me. So the atom is the smallest electrically neutral unit of an element, and it can't be decomposed into simpler elements by normal chemical means. It can be decomposed into other components. These components, protons, electrons, and neutrons, but those are not elements. Those are something different. There's a different state of matter. So that's what an atom is, and the key phrase here is smallest electrically neutral unit. So how did I know that this had 6 protons? Because it had 6 electrons. The electrons are all -1. Therefore, since it's electrically neutral, it must have 6 plus 1. That means it must have 6 protons. So that is what an atom is, and again, most of you have seen that sort of thing before. Now, here is an abbreviated periodic table of the elements of just the first 3 rows. And those first 3 rows are lovely for biologists because those are the only 3 rows we have to deal with. And in fact, the other nice thing about the periodic table that biologists have to deal with is that we don't have to worry about the transition metals and all the other nonsense in the middle of the table. And the reason for that is because essentially all of the elements out of which living things are made are here: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Chlorine, magnesium, sodium are also common, but they typically show up as ions. Ions are not atoms. They're sort of like, if you wish to say this is essentially correct, they're charged atoms. But they're not chemically atoms, they're chemically ions, because again, sodium, for example, has a +1 charge, potassium has a +1 charge, magnesium +2, calcium also +2, and chloride -1. The living things then, none of them are transition metals, and none of them are up in the upper rows. The lower rows, the higher rows. It's only these elements that we really have to deal with in living systems, and if you want to remember it, just remember the word schnapps. There it is. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay, so of all of these things here on the periodic table, the ones that are highlighted, what of these are the most abundant elements in living things? What is the most abundant thing? There's 2 ways to look at that. One is how many of a given atom are there, in which case hydrogen is the clear winner. There's way more hydrogen than anything else in a living system. The other is what makes up the total mass of a system, the greatest amount of mass of a living system. Now, most people would probably say carbon, because we're organic. That's what we just said. We're looking for carbon-based chemistry, so therefore carbon should be the one that makes up most of our mass. That's not right. Interestingly enough, what makes up most of our mass is oxygen. And if you think about it for just a moment, that actually makes perfect sense. Your body is mostly what compound? Interestingly enough, your body is not mostly an organic compound. It's mostly the compound water, which is not organic. There's no carbon on it. Water is H2O, and oxygen is much heavier than hydrogen. How do I know? Because its nucleus is much, much bigger. It has many, many more protons than hydrogen. We'll get into that here in just a moment. But that means then that the majority of your mass is actually oxygen, not carbon. Carbon comes in second by mass. So here, oxygen makes up about 60% of your body mass. Your body weight is about 60% oxygen. Only 18% is carbon by mass. So what are all of these things then? So this CH4, NH3, H2O, O2, and so forth, what are all those? Well, all of these then are what we call molecules. This is a molecule. These are all molecules. This is the molecule methane. This is the molecule ammonia. This is the molecule water. And this is the molecule molecular oxygen. So what is a molecule then? By definition, technical definition, is a molecule is again the smallest electrically neutral structural unit of an element or compound. Again, it's electrically neutral. It's the smallest unit of an element or compound that you find naturally in its structure. So notice, molecular oxygen is not the element oxygen, it is the molecule oxygen, because this is how you tend to find free oxygen. Oxygen tends to bind to itself and form this structure right here. This is what we call a space-filling model of oxygen. This is a ball and stick model. This is the structural formula. This is the molecular formula. So that's the key point, is that these are structural units. They're different elements, sometimes the same element, different atoms of the same element potentially bound together, or different atoms of different elements bound together, like here, hydrogen and carbon in the methane. But the bonding is the key. What kind of bonds are made here? The 2 kinds of bonds that make molecules must be strong, and the 2 strongest bonds are covalent and ionic. Ionic has higher binding energy than covalent, but most of your metabolism is in fact based on covalent bonds. So that's what I need to get into next. What exactly is it that causes covalent bonds to form? And that's what we'll talk about here in a moment.